like hitting a wall in a complex math problem where an exact answer feels just out of reach. Today, we're diving into a really fascinating area of mathematics. It sort of redefines what's possible when it comes to solving equations previously deemed, well, unsolvable. We're talking about high degree polynomials, those formidable equations where x is raised to a really big power. For a long time, mathematicians have had to rely on approximations for these. But our sources today introduce us to a groundbreaking method, the Ezouidi's theorem.
Yeah, and what's fascinating here is how the traditional methods, like a numerical approximation such as Newton's method, they often fall short. I mean, they give us estimates, which is useful sometimes, but they always come with that inherent risk of rounding errors, little inaccuracies that can build up. And then you have Abel's theorem, which is quite famous. It basically states that certain polynomials simply cannot be solved using what we call radicals. So that means solutions expressed just with addition, subtraction, multiplication, division, and nth roots like square roots or cube roots. But Ezouidi's theorem, well, it steps in contrary to Abel's assertion, actually offering exact symbolic solutions. It's a completely different way of thinking about it.
Okay, so our mission in this deep dive is to unpack this powerful theorem. We want to explore how it derives these precise answers for equations that have historically posed, well, huge challenges. We're going to walk you through a truly impressive example, solving a polynomial to the power of 19. It sounds incredibly daunting, I know, but you'll see how this approach systematically finds exact values. And that kind of precision can be critical in fields from, say, cryptography to high precision physics. Right, so to really appreciate this breakthrough, let's look at the kind of challenge that mathematicians really scratching their heads. Our deep dive begins with a truly formidable opponent, maybe we can call it a beast, a polynomial with 20 terms, an x to the 19th power. And the coefficients, they stretch into the millions. Just imagine trying to solve that by hand or even with traditional software that relies on approximations. So this specific polynomial is px equals. Okay, bear with me here. Beta 19 Laura, 19 by 18, plus 171 by 17, 969 by 16. Keeps going. All the way down through terms like 831, 392 by 9, plus 4081, 303 by 8, minus a whole bunch of other terms until you get to plus 415, 6794 by 2, plus 0x, 831375. It's massive. And as you can imagine, it's coefficients of these L values. The open Q is 19, L1Q is 171. All the way to LHN Q is Z31375. They just make it incredibly complex to look at.
Yeah, it really does. And this raises that really important question. How do you even begin to get exact values for x in such a complex equation? Especially when, like we said, numerical methods only offer approximations with those potential errors. That's exactly where Ezouidi's theorem fundamentally changes the game. It offers not just an answer, but the precise answer. The core brilliance, really, of Ezouidi's theorem is its departure from approximation completely. Unlike those traditional approaches, my method reveals the exact symbolic roots, and it does it through a structured, recursive process. It essentially bypasses the limitations you hit with classical algebra and numerical methods. So, this isn't just a numerical estimate, it provides precise, solvable roots.
Okay, and here's where it gets really interesting for me. The theorem demonstrates that even polynomials with radical roots, the very ones Abel's theorem suggests are unsolvable by radicals, can actually be solved exactly with this method.
Precisely.
It's like finding a secret path through a mountain range that everyone thought was impassable. It's not about getting close enough, it's about absolute precision.
Exactly. And the theorem works by expressing the polynomial in terms of a new set of symbolic coefficients. We call these say 1q. And these are recursively calculated. You can kind of think of it like a chain reaction. Each new coefficient is precisely determined by the ones that came before it, along with the original polynomial's numbers. It's a very structured, step by step process, and that guarantees exactness at every turn. Now, the specific formula involves things like binomial coefficients and careful indexing, which looks a bit complicated on paper. But the essence is that it's a completely deterministic process. You're moving forward with unwavering certainty at each step.
So, what's the fundamental power of having each coefficient determined symbolically like that, step by step?
Well, it ensures that at no point do we introduce any rounding errors or approximations. None at all. Every single value we calculate is an exact mathematical expression. We're building precision upon precision. And that contrasts really sharply with numerical methods where, each calculation, especially with long decimals, can introduce tiny inaccuracies that just compound over time.
Okay, so applying this recursive calculation to our big degree 19 polynomial, that must yield some pretty interesting results for these East values. The process involves systematically calculating each one, right? From K0 all the way up to K19.
Yes, and remarkably, when we calculate these is coefficients, we find a very distinct pattern emerges, a vast majority of them beautifully simplified down to zero, specifically 0 through S7. all
Right.
0, then S8. That takes on a precise value. It's 92377 divided 199, a specific exact number. Following that, S9 right through S16 are also all 0 again.
Wow, a lot of zeros.
A lot of zeros. Then we hit S17, which is another significant non-zero value. 923,751, 1918, exact again. And finally, S18 comes out as 0. Now, this isn't just some random numerical outcome. This specific pattern, the zeros in these particular non-zero values, is exactly what sets the stage for the dramatic simplification that's coming next.
Right. And this exactness isn't just a numerical result, is it? What does this precise calculation actually mean for the next step in solving this beast of a polynomial?
Absolutely. It's not just about the numbers themselves. Because these S coefficients are exact symbolic values, they allow us to rewrite the entire original polynomial in a fundamentally simpler form. This isn't an approximation or anything like that. It's a purely algebraic transformation made possible by the theorem's recursive structure.
Okay, now for what sounds like a truly aha moment. With these specific symbolic S values calculated, the real magic of Ezouidi's theorem starts to reveal itself. The original, incredibly complex degree 19 polynomial, when you express it using these new S coefficients, simplifies dramatically.
That's right. If we focus on just the terms involving those non-zero coefficients we found, S8 and S17, the polynomial px transforms into this much, much simpler form. Px equals x a theta by 9 plus S17r E0.
Hold on. That's an incredible simplification just like that. So this transformation means we immediately see one root just pop out. X equals 0.
Exactly.
And the remaining part of the equation, that by 18 area by 9 plus S17R term inside the parentheses, well, that looks like a far more manageable equation to tackle.
Indeed, it is. The simplified equation by 18 heirs by 9 plus S17r is 0, 0, where is actually, well, it's basically a quadratic equation if we think of by 9 as our variable. It's a clever substitution, really, that unlocks the solution path.
Oh, I see, like substituting y for by 9.
Precisely. And by substituting the exact values we found for SR and S17, or we get by 18 plus 92377, I won 199 by 9 plus 92375, and 1918 equals 0. So now we can just use the standard quadratic formula that everyone learns in school, but we're solving for by 9. The discriminant calculation involves that term minus S1R, which we know is 8529815.125, diamond 1918. It's a big number, but it's exact. This gives us by 9 equals NHR4 tar. Again, all precise values.
Okay, and so here's the final precise solution for x. It looks like .xk, where k runs from 0 to 8, giving us 9 roots from this part, equals 219 E2ki 9.
That's it. These roots are expressed in terms of complex exponentials, which is a direct and perfectly exact outcome of the recursive steps. What's really fascinating here is that we have completely bypassed numerical approximations. Every single one of those 19 roots, including the exeb that we found earlier, is now known with absolute precision. And that's something traditionally considered, well, impossible for such a high degree polynomial using just radicals.
Now, what's truly remarkable, I think, is how this method provides its own kind of internal validation. Our sources highlight a fascinating calculation involving a term called sigmac. For k going from 0 to 17, sigmac is defined as L0q plus xk19.
Yes, and when we apply this calculation, particularly for sigma using one of the roots we found, it simplifies beautifully down to just 1. Now, this isn't just a neat coincidence, it's actually a powerful internal consistency check. It's almost like the theorem inherently verifies its own results as you go along. It confirms that the entire recursive process is holding together perfectly and precisely.
Okay, so we've walked through this incredibly precise process. We went from a monstrous polynomial to exact symbolic roots. But let's bring it back. Why does this exact symbolic approach matter so much today in an age where we have powerful computers that can give us really good approximations? What's the true implication here?
That's a great question. It matters because exactness means zero rounding errors, no uncertainty, no accumulation of tiny inaccuracies over complex calculations. This is a level of precision that really redefines what's possible in fields where absolute accuracy is absolutely paramount. Think about things like cryptographic algorithms. A single bit error there could compromise security entirely. Or high precision physics simulations modeling fundamental forces, or even long term orbital mechanics calculating paths of planets or satellites, where even tiny rounding errors can compound dramatically over years and decades, leading to completely wrong predictions. This theorem demonstrates that even for these high degree polynomials, the ones deemed unsolvable by classical methods, exact solutions are actually within reach. It's really a testament to the power of structured, recursive problem solving. And maybe even a philosophical shift, moving from settling for good enough towards achieving perfectly precise.
So to recap, we started with a truly daunting degree 19 polynomial, an equation that frankly, would send shivers down the spine of classical numerical methods. But using Ezouidi's theorem, we've seen how a systematic recursive process can kind of peel back the layers of complexity and deliver exact symbolic solutions.
Right. It's a powerful reminder, I think, that the perceived limits of mathematics aren't always fixed. They can always be challenged by new ingenious approaches. And this isn't just about solving one specific polynomial, however complicated. It's perhaps more about a philosophical shift in how we approach mathematical problems, generally actively seeking precision over approximation whenever possible. It really makes us rethink what we believed were fundamental barriers, doesn't it?
Absolutely. So, after witnessing the power of Ezouidi's theorem today, you might be asking yourself, what other unsolvable problems out there, maybe in mathematics, maybe in other fields entirely, might simply be waiting for a clever new method, a different perspective to reveal their exact solutions? And maybe on a deeper level, how does understanding exactness, even in a world full of powerful approximations, redefine what we truly value in knowledge and discovery? Something to mull over until our next deep dive.
Hello again. As you see, we already solved the 19th degree common equation, and this is the exact sum roots for 1 to the power 19. The roots here, my colleagues have expressed in terms of complex, exponential, and Arabic with a direct outcome of the recursive steps we have to know. As you can see, Ezouidi theorem doesn't rely on numerical approximations. The roots we have derived are exact, not subject to the proven calculations that come with numerical methods. This approach assures that we can find the roots exactly, even for high-degree common equations that are too complex for classical method to handle the exact roots. But you can see Ezouidi Muratsukan theorem can do this. The roots here are derived recursively, where we solve for them step by step. This formula breaks down the polynomial into manageable components, allowing us also to derive exact sum with very specific approximations. So thank you for listening and see you next time. Thank you. Thank you.